Okay, Chapter 4, Network Fundamentals. Many of you, maybe most of you, have had Network Plus or significant networking experience. So this is kind of a quick trip through networking. In networking, we use the model, the OSI model, and the functionalities of the different hardwares to put the network together. So we've got the network together. Now we need to try to make the network secure, and that's what this is about. The network components, what we can do with them, what we can't do with them, IP addressing, and we're still going to focus on IPv4, although we really are getting more and more and more into the IPv6 world. And then the ports and the applications. Ports obviously associated with applications with the IP address, and the port together we get a socket, which gets us to a location and a service. So we're going to talk about the OSI, the TCP/IP models, the data link layer technologies and devices, and I want to try to do some demos with these things. The data link layer, I use Packet Tracer, look at the switches, look at the MAC table, how we get the MAC addresses again, the different processes that we can use, and then how to make it secure, because we can do some security applications or apply some security at layer 2, at the data link layer in the switch itself. And then the network layer, protocols and devices, and then non-IP networks and network convergence. And that's going to be the same as it was in Network Plus, the VoIP and the industrial controls that are now there. So the OSI was created by the ISO, and yeah, those are not the International Standards Organization is the ISO, and ISO is, I think it's Greek for modular parts or components or something like that. But that's what the model's all about, is being able to have multiple layers do different things. And we talked about that. And that is happening to us today, because we're in the process of migrating from Internet Protocol IP version 4 to IP version 6. And the only thing that really changes is layer 3, the networking layer, where the IP addresses are. The media didn't change. We're still using twisted pair or fiber, or if you're really lucky coax, or we're using maybe leased lines, or we're using a cable modem, or you're using DSL. All of those things stayed the same. We're still using switches. We didn't have to go out and buy new switches. What we had to do was to get the support for it in the NICs and in the operating systems at layer 3 for the IP addressing. To go above that, TCP is still the same. The applications are still there. We're still using web browsers, and we still have email servers and web servers and database servers and all of those things. So the modeling is something that makes the changes in the network easier to manage or comprehend when we do those things. The important educational and a theoretical tool, and it is in fact a theoretical tool. The OSI isn't really the way that things work. When the OSI was developed, NetWare, for instance, already had a model, and it was a 3-layer model. But we have that. The TCP/IP, the formerly known as the DoD model, actually was designed to chart the flow of TCP/IP. Designed by DoD, by the Defense Advanced Research Projects, the DARPA, maintained by the IETF, named for the two most important protocols, TCP and IP. TCP, UDP being the two that are the two transport protocols. UDP not used as much as TCP. The dominant standard of the internet. It's the thing that we really use, although when we start talking about troubleshooting and all of the other parts of networking, we always refer to the OSI layers of these things. And keep in mind that networking itself, when we look at the model, networking itself really only goes up to the layer 4. All of the other stuff, the top 3 layers, are really part of the application. They're kind of more related to the computer than to getting data from one point to the other. And if you do the Cisco courses, the router courses, that's what we're concerned about: shipping data, getting it from point A to point B, making it secure. The web browser working, the email server working, all of those things are more a function, or actually are a function of the devices themselves. I've got a couple of slides here on the OSI model, and I think that maybe everybody does or maybe everybody doesn't. The way that or at least the way that I remember it, is with the little saying, please, and I'm going to go from the bottom up. Please, P-L-E-A-S-E. Please do not throw sausage, S-A-U-S-A-G-E, sausage pizza, away. So the first letter of each of these words represents the first letter of the layer of the OSI model. The other one that's been published for years is all people seem to need data processing. So first thing is, what are the layers? Where do they go? How do they work? What do they do? The physical layer, the connections between the devices and the physical media. And this says connection. The media itself is just something that's kind of there. What this is the way that we send the data. What are the voltage levels? What kind of connectors do we have? Those are all defined at the physical layer. The data link layer, 2 directly connected nodes. If we go in with our switches and we put our devices on them, these are all going to be layer 2 connectivity. And in here, in the data link layer connecting the nodes together, we have an address, a fixed address, a physical address called the MAC address, the Media Access Control, which is a 48-bit hexadecimal number. And if you want to see what yours is, you can do an ipconfig all on your machine and it'll show you the physical address. The physical address is unique, and it should be unique universally. It's broken down into 2 parts, the OUI, the Organizational Unit Identifier, and then a serial portion of it. So they should be unique around the world. And these are the addresses that actually are used to do final delivery of the data. It's kind of like the mail system, we're going from the wrong end up, but the physical device would be your house address, and the delivery would be the mail carrier with an envelope that has your name and address on the envelope, puts it in your mailbox. So the physical address, the one that is used for the last delivery. The network protocols for transferring data to nodes with unique addresses. And say, okay, you just told me that we had the physical address was unique. We do. And we also have this network address, this IP address. The IP addresses can change, and they do change. They don't change real frequently, but they can and do change. What the IP address is really used for is if we had, let's say something in, let's see, we have Dallas. We'll have something in Dallas and something in Jacksonville. And this would have an IP network, and here would have an IP network. What the layer 3 does is allows that traffic to travel from Dallas to Jacksonville, Jacksonville to Dallas. Once it gets to Jacksonville, the individual machine in here is going to have an IP address. And it's also going to have a MAC address. The IP address may or may not be the same IP address that it had yesterday, but this is the one that it has today, and that's where it went to. What the router, layer 3 device, a router is the things that allow us to get traffic from one location to the other. The router is going to ask which MAC address has this IP address using a process called ARP, the Address Resolution Protocol, which is an IP to MAC resolution. Once that happens, the router will then send it to the MAC address that it's intended for when we do those things. The transport protocol, the transport layer, controls the reliability of data transmissions between nodes. And I think we're going to look at some of those, and I'll do the whole thing here. What happens with TCP? TCP is the one that's going to be our reliable protocol. It establishes a connection, much like you would do with a phone call. For people that still use phone calls, I know most people are texting today, but it uses a process called a three-way handshake, which is a SYN, a synchronization packet, a SYN-ACK, and then an acknowledgement. The ACK is acknowledgement. What it says is, hey, I want to have a conversation, and here is my numbering system, because I'm going to number all of my data packets that go from me to you to be sure that you got them all. That's where the reliability comes in. The other guy acknowledges my synchronization signal and says, well, I want to have my own numbering system so that it numbers its packets. And that's the way that we get the reliability, by numbering the data that goes from one location to the other. Once it gets there, the session, consistent connections between devices. You say, well, you just told me the transport layer did that. The transport layer is going to connect between two locations, let's say. And we might have a web page open, and we might have maybe a file transfer, or we may have an email. So what the session layer does is controls the sessions, the applications that are communicating with each other from one to the other. The presentation transforms the data into formats that are understood by the software. The presentation layer checks to be sure that the application layer can understand what's going to it, and it can transform things, or it can just simply send them up. And then the application enables the interaction for the software. Applications are services. Here we might have a web server, or a file server, or a mail server. And that's going to be on the server side, obviously. On our side, we might have like a browser, and the browser would connect to the application layer, go down the stack, get the different headers, and we'll look at some of this as we get into it. Different headers put onto it to get it sent across the network from one location to the other. So the application layer, each layer communicates with the layer. Layer 7 communicates 7, 6 to 6, 5 to 5, 4 to 4. And each layer supports the layer above it to be sure that things work. So if something doesn't work down here at the physical layer, it's not going to work anyplace else in the stack. If we have an issue at any layer, it can disturb the things at the layer above it. This image, and I think this image is, it's in the Network Plus, and it's obviously here, but this is a pretty good summary slide about what goes on in the OSI model. The physical layer, media signals, binary transmissions, the protocols are the things that are there: RS-232, RJ45, RS-232 is going to be the serial connector, DSL 802.11, wireless. Those things are all going to be at the physical layer. The data link layer, it says router MAC, the MAC address. Switches are going to be at this layer. Ethernet, VLAN spelled wrong, ATM, fiber, frame relay, HDLC. Those are encapsulation protocols that are used at layer 2. And then we go on up. The network layer, path determination, and the data link layer, physical addressing, the path determination and logical addressing. The IP addresses are logical addresses. The MAC addresses, the media access control addresses, are physical addresses. They don't change. IP addresses don't necessarily change, but they certainly can change. And then the transport layer, end-to-end connections and reliability. We're going to number everything. It's like the numbering there. When I was in the Navy and deployed, we didn't have all the fancy stuff that people have now, like email. We had a stubby pencil and a piece of paper and an envelope to send information back home and to get information from home. So what you would do would be number the letters so that my wife would know if she got them all, would know if they were out of sequence, so that, this doesn't make any sense. Well, you're reading letter 5 and you don't have 3 yet. So that's what this end-to-end and reliability does. When we number the data packets, not only can we be sure that all of them got there, but also that if they got there out of sequence, they can be put back into the proper order. The session uses this as inter-host communication. This is going to be application to application for these things. The presentation layer, data representation and encryption goes here. So if we encrypt things, we're going to be doing it at the presentation layer, recognizing data, HTML, doc, JPEG, MP3 sockets. Its responsibility is to be sure that the data that's presented to the application layer can be read by the application layer. And then up there, the network process to the application, DNS, www, web servers, email, telnet, FTP, different applications that are available. And those are, in fact, services that are running on the devices themselves, not applications like Excel, Word, those sorts of things. The applications here are web servers, email servers, file servers, database servers. Those things are going to be running at that layer. Another kind of what are these things? And we encapsulate information from one to the other. And I keep saying that. Let me do a Wireshark here so we can look at kind of what some of this might look like as I overload my machine here with the things that I've got going on. So let's look at maybe TCP scan. So what we have here is Wireshark, which is a sniffer, a protocol analyzer, lots of different terms. What it does is looks at traffic that's on the network. Well, I talked about, and there's a three-way handshake in here somewhere. Here we go, a three-way handshake where we start up, and this is 192.168.100.150, the IP address connecting to this location, the synchronization packet. And it actually tried to start the conversation twice here. And it finally did get the conversation started. Let's see, 6 on this one. So the sequence number here, the numbers, we don't use 1, 2, 3, 4, we use really big numbers. And what it does is acknowledge. What this says is, here we sent 667. Hey, I got it, send 668. And I'm just looking at the last 3 digits of this. And oh, by the way, I want to have my own numbering system. So down here, we say, the next sequence is 668. We acknowledge from 663. I got 663, send 664 when we do those things. When we look inside of the packet, layer 2, Ethernet, which is going to have MAC addresses on it. The OUI, this is a Belkin router and this is a Dell computer, but the addresses, the MAC addresses, the full ones are here, 94:10:3E, 6E, 48, 88, and on down the line. So we have the destination and the source MAC address, and these are any flags, and there are no flags set on these things. And it says, hey, the next thing that you're going to see is IPv4. This is an IPv4 packet. So we go from the Ethernet layer, layer 2, the data link layer, up to the IP layer, and in it, there's not any real data in these things, but we have the source and destination address in here somewhere. Yeah, right here. Source and destination address are in here, and then other flags that might be set. The time to live is significant. How long can an IP packet exist on the internet before it dies? And this is 120 time to live 128. It's 128 hops, which is basically can go over 128 routers before it goes away. And its next protocol is going to be TCP. And then we get TCP down here, the transmission control protocol, the transport layer protocol. And we have a source port, and we'll talk about ports a little bit later tonight, and a destination port. And you can look at the destination port everybody's had. Network Plus says, oh yeah, that's going to a web server. And then the sequence numbers that go along with it. If we go down here and try to find something that's actual data, when we go to the bottom, actually this one doesn't have any actual data in it. Try to find something with actual data in it. Yeah, this one actually does. This is an XML message over here. So it actually has data. So the data gets encapsulated or gets all of these different headers put onto it. So we have the data comes down from, in the TCP IP, we're going to say the top three, we just all lump together, to the HTTP, to the IP, HTTP protocol here, to the transmission, HTTP, we're up at the application layer, and then we put a source and a destination port on it, then we put an IP address on it, then we put a MAC address on it to get it from one location to the other. The IP addresses are used by routers to go across longer distances. So these things, the applications on a node to request network services such as file transfers, email, database access. Layer 6, the presentation translates the application layer into an intermediate form that both the client and the server can process, something that they both understand. The session layer establishes and controls data communications between applications operating on two different devices, regulating which device can send data and how much it can send. It says, okay, you've got, 2 microseconds or 40 milliseconds or 5 seconds or whatever. Okay, you're next, kind of thing. It controls the communication between the applications. The transport layer, the establishment, maintenance, and teardown of the connection between the two locations, the two devices themselves. The network layer, logical addressing, IP addressing. The data link layer, the physical address, and down at the physical layer, the transmits the bits, the ones and the zeros actually get put onto the media. Here it can be fiber, radio for wireless, or it can be copper wire, RJ45s. So the OSI layer, and then I got a bunch of these. What this one it shows is that each layer, adjacent layers, well, that's not adjacent, are they? Each layer communicates or talks directly to its equivalent layer. The application layer to the application layer, data link to data link, physical to physical, network to network layer. And each of them, also the adjacent layers, each of them communicates with the layer below, above it. Over here, layer 1 supports the layer 2 information, supports the layer 3 on up the line. Each of the layers of the model support the layer above it. We've talked about the OSI, the TCP IP model. The functionality is the same. The way it's broken up is a little different. Over here, the TCP IP model, the top 3 layers are just called the application layer because these things all work in conjunction with each other. The session, presentation, application, and they're kind of dissociated, they're disassociated with the actual transfer of data from one location to the other. The transport layer, still a transport layer, although in a lot of them they're now calling the transport layer in the TCP IP model the host-to-host layer. The network layer is called the inter-network layer, And then the bottom two layers, the data link and the physical, are grouped together as the network interface layer, or sometimes called the network access layer. Over on the left, the protocols that are going to be running at each of these layers. The application layer, same thing, file server, web server, DNS server, the transport layer, TCP, the protocol TCP, UDP. UDP works here too. UDP is really intended for streaming. It doesn't have any of the three-way handshake. It doesn't have any of the acknowledgments. It's kind of a send it and forget it, a shoot and forget sort of arrangement with these things. The internet layer, or the network layer, IP, is the protocol that we use today because it's the protocol of the internet. There used to be others. IPX or NetWare would have been one of them, and IPsec is there. The network interface layer, Ethernet, is the protocol that we use on our local area networks. ATM, asynchronous transfer mode, and frame relay would be wide area network encapsulation protocols that would be used at layer 2, or the network interface layer on these things. Another, the 4-layer model, application data, and then the little red boxes represent the header information that we saw in the Wireshark scan. The network access, the data link layer, you don't see everything. It's got a start a frame, and then it's got at the end it's got a CRC, a cyclical redundancy check, to be sure that nothing got damaged or changed en route. Basically damaged en route. So the header information, the datagram, we have the application data in the header, datagram in the header packets. We keep putting header information on these things as it goes down to the stack. As it goes up the stack, we strip that header information off, and until we finally get to the top. I like to think of this as, we're using quite a bit of overhead to get a little bit of information from one location to the other. So the purpose is to get it there in a timely, orderly manner where it makes sense when it gets to the other place. More of these things. The application layer for the TCP/IP model allows the user-level applications to access the other layers protocols like HTTP, FTP, IMAP, POP, and SMTP. All those letters: HTTP, web server, hypertext transfer protocol; FTP, file transfer protocol; IMAP, internet mail program. I've forgotten exactly what it stands for. POP, post office protocol; and SMTP, simple mail transfer protocol. It's the one that sends. IMAP and POP get email. SMTP sends email. The transport, or the host-to-host layer, manages the end-to-end communication, breaks applications into segments or datagrams. TCP and UDP are here. The internet controls the routing of packets across multiple logical networks. New term there, logical addresses, IP addresses. Logical networks are created by these and controlled by them. IP and ICMP protocols are going to be here. The network interface, or the network access layer, how the nodes on the local network and adapter level communicate with each other. Ethernet, Wi-Fi on Ethernet or Wi-Fi on local area networks. Protocols like PPP, point-to-point protocol, frame relay, ATM. And these are just should all be basically letters to you that, okay, yeah, I got this. Point-to-point protocol, frame relay, they're encapsulation protocols that allow us to send the data, put it in the package, just like the letter goes in the envelope, put it in the package and get it from one location to the other. Because at the end of the day, when we are, regardless of how far we are going, and we have routers here that we're going from, well, let's go from Dallas to Jacksonville again. We have obviously more routers than that, but when we go from one location to the other, we'll go from the Dallas router to the next hop router. So we're going from one to the other, and we're going to be using the MAC addresses to get from one to the other. When we get here, it's going to be a point-to-point connection. When we get here, it's going to be a point-to-point connection, and we're going to use these MAC addresses, and route tables tell us where to go to in order to get from Dallas to Jacksonville. So layer 3 tells us how to get there, and layer 2 actually drives us there from one location to the other, from point to point. Multiple point-to-point links when we go from one to the other. So we have all of this stuff. Easier to identify the threats. Understanding the layers makes it easier to identify the threats and the targets. It does, kind of, sort of, at least. What we got to understand is what are the threats at each of the layers, and help us secure it by layer. If layer 1 fails, the rest of the network likely will fail. I always figured that anything that I could stop at layer 2, I didn't have to worry about at layer 3. I didn't have to worry about it at the application layer, because if you can stop the attack there, it doesn't go any further. If an attack succeeds at layer 7, the bottom layers is going to be unable to stop it. So if we have an application attack that is successful, then everything else is going to kind of follow in its way. Protection that can happen at each of these layers. At the application layer, proxy servers. And a proxy server, and this is there and the presentation layer. A proxy server is something that does something for you. It's like any other proxy. It acts on your behalf. What we do with proxy servers, if we have us and our proxy here, and we have the internet out here, because I can never really draw a cloud. We'll try a cloud. See why I don't draw clouds? We go to the proxy server and say, hey, I want to go to some website. The proxy server takes our request, rebuilds a new request, and goes to that web server. Answer comes back to the proxy server. Proxy server then rebuilds the answer and sends it to us. So we have this point of isolation in here where we can scan, we can look for viruses, we can look for spam, we can look for all sorts of things on the proxy server before it actually gets into the devices itself. Yes, it is a new packet. It rebuilds the whole thing. If this IP address is 192.168.1.1 and this one is let's say it's 72.12.16.4, we'll go to the internet from the proxy server's IP address. A couple of advantages here. One of the advantages here is that everything appears to come from the same IP address from the proxy server, so that the bad guys, somebody out there doing scanning or looking at doing reconnaissance or surveillance, can't really get an idea of how many devices are on the backside, because everything comes from this single IP address. And it goes back here, rebuilds a new packet, and then goes to the internet, comes back and rebuilds the packet again and sends it back here. Advantage to this, just like when we're going to talk about firewalls where we can filter things, we can filter things with a proxy server. We can do things like word filtering. The only problem is, and we used to use these because early on in the internet, and it was mostly the male students, just couldn't stay away from pornographic or pornographic related sites. So we put in a proxy server and we filtered IP addresses. You can filter on IP address. You can filter on words. The problem with words is if you filter the character string, and I hope I don't offend anybody, then you also, because part of it, if you went to Sussex, England, you would also filter this out. So you have to be real careful about the things that you do there. We'll make that word go away. So it does these things. Application proxy servers run here. The other thing that you can do with these, now that I've got everything drawn here, if we have we'll use the same proxy. If we had something sitting inside here, let's say we had a web server inside here, and we didn't want to let all these people on our network we could have a proxy go from outside in as well as from inside out. It's called a reverse proxy. So we could go either way with the proxy. Session layer and transport layer, firewalls, we filter here. And at this layer, we're going to filter on the TCP ports, and the IP addresses down here. We go with firewalls down through the layer 3 also. Layer 3 routers, we can filter on them with IP address, and we can filter with only IP address if we want. Data link layer, we can filter with the MAC address. And we're coming up on a break, and we'll look at how we do that in a minute down here. Hubs, repeaters, patch panels, cables, and network cards are the devices that run at that physical layer. And the physical layer is really just connectivity. And the thing that we want to be sure here is that our media is good, the connections are good, because somebody disconnects something, creates a denial of service attack. The things, the little tabs on the RJ45 sometimes break off and the wires back out. Those are kinds of things, mostly physical, that's going to happen down here with these. The devices, data link switches, bridges, and access points. Layer 3 switches, routers, and firewalls are the devices at the network layer. And then we have firewalls at the transport layer, and then the proxy servers on up the line. So continue with this. So the TCP/IP communications, as constructed, really isn't very secure. Based on a concrete interaction between two protocols, it was robust in principle. It says that this send data strictly, and basically you want to follow the rules when you send it, but you'll accept anything. It's vulnerable to attacks, and we've seen or talked about some of those things in the networking classes. But we can intercept but not encrypted by default. So the telnets and the FTPs of the world, the file transfer protocols of the world, the data is in clear text. A lot of passwords get sent in clear text, unless if you want to scan your own network and look at if you're using Outlook, you're probably sending passwords in clear text on your own network. Not that big a deal on your own network, but it would be if you were using it, let's say, on a LeaderQuest network to do those things. So non-standard data. Send newer protocols. Some of the newer protocols are less trusting, IPv6. And after I said that, and Bell's going to say, am I sending my password everywhere? Because I bet they're using it. We're going to show in a minute why everybody's not seeing your password, because there are other things that happen. It depends on what you see, what kind of tools you use in order to do that. And then the box, TCP implementations will follow a general principle of robustness, be conservative in what you do, liberal in what you accept from others. And John Postel, who was early on in the development of the TCP/IP protocol. So strict in what we send, liberal in what we accept. So we'll accept things that maybe don't meet the rules, and things that maybe don't meet the rules can be dangerous to us. The data link layer, and then the data link layer, we say here, layer 1 and layer 2, the simplest. And honestly, if you look at all the things that happen, they're not exactly the simplest. You think they would say, oh, we're going to change it to ones and zeros. But we have to figure out some way to put those ones and zeros. What process do we use so that they're going to be readable when they get to the other end? What's the voltage levels going to be? What kind of media are we going to use? Is it going to be fiber, what light signals? Is it going to be copper? Is it going to be wireless? What kind of signals are we going to use? So a lot of things go there, but layer 1 shovels data. It puts the data on the media and sends it from point A to point B. Trust the higher layer protocols to figure out how to get there, what we're going to do. Layer 2 has multiple functions, and we'll look at some of them in a minute a few seconds here when we do those things. The data link layer combined with the physical layer in the TCP/IP model. In the OSI model, it's a standalone. Contains the technologies that can handle addresses, traffic direction, and a little bit of security. The MAC addresses we saw in the Wireshark, so we're going to use fixed addresses, MAC addresses at layer 2. Switches and bridges. Bridges are an older device, and switches were a follow-on to bridges that separate things. We have collision and broadcast domains here, and I think that I've got a slide here in a minute. I want to demonstrate collision domains. And virtual local area networks exist at the data link layer. And a virtual local area network is where we, with commands, break the switch up into layer 3 portions, components, local area networks. And wireless access points also work at the data link layer. The MAC address, the physical address, and if we look at it, let me see if I can get one up here. If you'll use the ipconfig all command on your machine, and mine has a whole bunch of IP addresses because I've got some virtual machines running on it. But the physical address here, this is the MAC address, the physical address of this device. Each of them has each device has a physical address, and it needs to be unique. It's again the thing that gets us the information that we need. 48-bit hexadecimal. The first half, the OUI, the organizational unit identifier. The last half is the ID. Used for address filtering. And MAC address filtering is pretty popular on wireless access points, on wireless routers. And we can use it there. We're also going to look here in a few minutes how we can use it on fixed addresses too. And then the EUI64, this EUI, Extended Unit Identifier, is what it stands for. Keeps showing up. It's kind of a Cisco thing that is uses the MAC address, the 48-bit MAC address, to produce the host portion of an IPv6 address. And it needs to be 64 bits in order to do that, so we add some information in the middle and FFFE in the middle in order to bring it up to the 64 bits. We would then append that to the IP address, giving us the 128-bit IPv6 address. A whole bunch of addresses in there. We're going to talk about IP addressing in a few minutes. Hubs and repeaters, and kind of jump back and forth, are devices that exist at layer 1. This is an Ethernet, a true Ethernet, which has all of these devices connected to a piece of cable, literally a piece of coax. And it uses T-connectors to do these things so that we connect these together. The collision domain says that if A wants to go to B and C's in here and C wants to go to D, who gets to transmit? Because both of them, all of them, can't send information at the same time. It's kind of like being in a room of people and, you know, everybody starts talking. If we start sending stuff here, A was going to B, right? And then C was going to D. You can't really understand anybody because everybody's talking at the same time. And when this happens, we get collisions. And when we have collisions, we have corrupted data. And then we have to start over. So what has to happen, and this is what's at layer 1, what has to happen is we have to have some sort of control. And that control happens at layer 2. And we call this process CSMA CD. Carrier Sense Multiple Access Collision Detection. What the devices do is if A wants to talk to B, the carrier sense there is a carrier signal here, just like there's a carrier, not a very good carrier signal. but like a hum, like what you would use with the radio in order, and then we're going to have to put in the data on it. So the carrier sense, multiple access, all these things are connected together. What they do is listen to see if anybody else is talking on the network. And if nobody else is talking, then A sends the information to B. And by the way, these things are going to be half duplex, which means that we can transmit and we can receive, but we can only do one at a time. And as long as nobody else talks while this is happening, the world is good. But let's say that C and D here were getting ready to have a conversation too, and they were listening. And at the same time, C sent information to D. Then we're going to have a collision. And when we have the collision, we're going to get a jam signal. And the jam signal tells all these guys, hey, there's a collision, your data got damaged, it didn't get there. So what they do is go into a random back off, and go through the whole process again until they get the data there. So collisions happen in true Ethernet. The control is at layer 2. Control is layer 2. There is no control at layer 1. It's the media, it's the signal, it's the voltage levels, those sorts of things. The control exists at layer 2. Now, this is, and the first network that I was on was coax. This is exactly what we had. Pretty slow, lots of collisions, and as you can imagine, the more devices that we put on here, the more collisions we're going to have, and the slower the network's going to be, because every time you have a collision, you have to do the back off. One of the devices that we said are here, and it would be a hub, and what a hub is we take this bus, and this is a bus network, put it in a box, and shrink it. The hub actually has a bus inside it. It doesn't use the T connectors and the coax. It uses RJ45, but it's still a bus, still has collisions. They actually have collision lights on them, and you can see them flashing all the time because there are lots of collisions in these. Fortunately, you're probably never going to see this. I hope you're never going to see this because it's a very, very old technology when we do those things. I got you, Adam. Appreciate it. The thing that we hope to see are switches. It says direct local traffic, create collision domains. It's really cool. Switches are cool, and this is actually a bridge down here. Switches and bridges. Bridges were the original switches. How's that? What happens here is we have the MAC addresses, and we'll look at the bridge and then we'll talk about switches. We have the MAC address. So what happens is the bridge makes a table of MAC addresses that are on this segment. These are called segments, so we're segmenting the network. And then we have the MAC addresses that are on this segment. Let's say we have A, B, C, D, and E. If A wants to go to B, it gets here to the bridge and it says, hey, I know where B's MAC address is and it ain't on the other side, so you can't go. If A wants to go to C, it gets here and the bridge says, okay, yeah, C's on the other side, permission granted. You can go across the bridge, so that we isolate some of the traffic that would be on the media when we do those things. We track address in a MAC table, relay broadcast packets, and broadcast packets, we keep having this term here, but broadcast packets are IP packets. So they're always going to go out of these things. Vulnerable to MAC spoofing. So I can simulate or spoof or change the MAC address, and there are protocols to do that, that we can spoof the MAC address. Why would you want to do that? So that you can get someplace that your MAC address isn't allowed to be. VLANs separate broadcast domains. Broadcast domains are going to be at the layer 3, at the IP layer. And I want to try to demonstrate some of this stuff in just a second after we say these things. collection of methods rather than a single standard. The VLAN's port-based dynamic and native untagged. I guess that maybe let's just go ahead and look at some of these things here. The first thing I want to look at is some security that we can put onto a switch, and this is what the switch would look like. We said we had a MAC address table. So if I show the MAC address table, I have the MAC address and then the port that that MAC address is associated with, so that when traffic comes in that says it wants to go to this location, it automatically goes to that location. Well, I think I want to do a couple of things. First, I want to erase the MAC. Erase the MAC. MAC. Now, erase. Oh, now erase. It's not going to let me do it, is it? It does that to me sometimes. Erase. Startup config. So let's try config 2. And I don't think that we can do that. Now, I'm going to have to get that one to where I want it to be, but we can demonstrate some of these things anyhow, because I think this one, and it may be because of the way I've got it configured. Yeah, this one doesn't have anything. So, how do these things get the MAC address table? This is Packet Tracer. We can do this simulation mode where we can actually see the data going from one to the other, and I constantly do this. So if I go from this PC, let's go to this one down here. We'll demonstrate some differences between, we've got a hub down here, hubs and switches, hopefully. If I go into the switch, I didn't have anything in the MAC address table. The MAC address table is self-populating. As the frame comes into it, it puts it in the MAC address table. So this MAC address is now on port FA03, Fast Ethernet 03. And I can keep going. It will then flood or send the frame out all of the ports except the port it came in on. And these guys say, hey, it's not to me, not to me, not to me. So we go to the hub here, and it sends it out all of the ports except the port it came in on. So this is finally the MAC address says, yep, this one is to me. So I'm going to send the answer back. And when I do that, you notice it went out here also, because on a hub it goes out all the ports except the port it came in on. And now, since I have gotten something in here, I now have a new MAC address added to my MAC address table. And when it went back to the destination, since the MAC address was in the MAC address table, said go out this port, it went directly out. If we keep going, do one more time, instead of going out all the ports, since the MAC address is in here, it goes out the correct port to it. But we have a problem here, because we don't have a problem, but that's what happens with a hub. It goes out everywhere. So how can we help ourselves at layer 2? There is a thing that we can configure on the switch, and this one is configured. It's called port security. Now what port security does, and one of the reasons I couldn't make it go away here is because I have port security configured on it. Show MAC address table, and we have these things. And if I looked at the configuration, these are now, the other ones were dynamic, they're going to time out. These are static, they're going to stay here. So what would happen to us is we would have students come in, and they weren't happy with the wireless, wasn't fast enough or whatever else. And they would plug come in, bring their laptop in and plug their laptop into the switch where our device was that we knew had a antivirus on it. We knew it was up to date. We didn't have any idea what's on this guy's laptop. So when we configure port security, this red says, hey, I just shut the port down. So port security can be configured on switches, and that's where the MAC filtering comes in, because a MAC address is now associated with a port, so that only that MAC address can be on it. Do we want to do, maybe want to do MAC spoofing in order to get onto those things? Yeah, there's a possibility that we would do that when we do those. The next thing is VLANs, and let me try to open a different file here to look at, because we say broadcast domains, and broadcast domains just simply mean where IP networks communicate with each other. I think this is the one that I want. So when we have a broadcast domain, and these have VLANs set up, and we got to wait for these to turn. It takes about a minute for these orange to turn green. This is another protocol that keeps switch networks from being nasty. And I was just seeing if I had something else down here, and I don't. Okay, so now we are in here. These guys are on the 192.168, 1.4, 1.2, 1.3, and 1.5. I want to put another machine on here, and I'm going to put it in a different IP network. And we'll do the little demo again here. And we'll put him on, these were all ones, right? We'll put him on a 192.168.5.1 network. We don't need any of that other stuff because we're not going anywhere, and we got to wait for him again. Now, let's see if we can make it a little faster. Okay, so we made that a little faster. If I send something to the broadcast domain, let's go back in simulation mode so that maybe we can see where these things go. Let me go back to real time. Let's see if we can move this over so we can see this. Let me move it down a little bit. See it a little bit better. Go to simulation mode, and I'm going to go in here and I'm going to ping the broadcast address. Okay, a couple of terms here. Ping is just a way to echo a request, and echo reply uses the ICMP protocol 168.1.255. A broadcast address says, hey, go to everybody that's in that IP network. So when we send these things out, it should go out all the ports. And it goes out all the ports, even to the one that it doesn't belong to, and it got the flashing here that says, yeah, not to me, because it's not on that network. These other guys are going to then start responding, and these are the answers. This is, you can see over on the right, I think it's given the protocol we're using, ping here. When we go again and try to maybe go again, maybe not go again. Yeah, I overstressed packet tracer. So it's going to be a few seconds here before it crashes on me. There it goes. It goes out them again because it keeps doing broadcasts. What we want to do with, back to real time, stop that, with VLANs is to create broadcast domains, and that's what the colors represent on the devices themselves. This one is the 3.5, so you can go in here in the simulation mode and we'll ping, do the same thing again here. Ping 192.168.3.255, because that was a 3 network, right? Now then, it only goes, I hope, to the devices in the green network, the green VLAN, Virtual Local Area Network. And we create these things simply by telling the ports on the switch that they're in those. So we can get separation, broadcast domain separation, have less traffic on the going to the individual machines by using the VLANs. So the VLAN technology. And these are just how we can do them. Port-based, dynamic. Port-based is when we go in and we manually put them in. Dynamic is if we have all of the equipment that we need to do that, they can be automatically assigned. And then protocol-based, voice over IP is what we're kind of talking about here. And then the native VLAN is a term. These are for all of the devices that don't know about the tagging, and this is what this is called, is VLAN tagging. Now we have this thing called a native VLAN, which doesn't have any tags on it, in order to allow all of these devices to communicate with each other. And this VLAN and the trunk, you saw that hopefully the traffic goes from one switch to the other switch. If I go back here and do this, 255, it goes from both switches. And what the trunk port allows to happen is all of the VLANs to go from one switch to the other switch. If I go down here and do the same thing in the blue VLAN, we're going to get that traffic only goes to its traffic. Now let's see if I can overload packet tracer here. So we'll ping 192.168.2.255 because this is the 2 network. And now then, we have lots of traffic going on here, going everywhere. But you notice that we're not having any collisions. Switches are full duplex. They can transmit and receive at the same time. And what the MAC addresses allow is for the quote switch, the ports on from one to the other when we do those things. I may not have this one over here configured correctly. Yeah, I'll do 2.4. Yeah, it got over there. It's just that it right now, the simulation, too much going on. It can't really do all of it at the same time. So we create broadcast domains, layer 3 domains with VLANs. And how do we communicate from one of those to the other? We're going to use a router in order to get from one to the other. So we have trunk ports which allow all the VLANs. We have VLANs which allow us to separate, and this shows down here sales, engineering, QA, finance. We can put each of the work departments in their own IP network, VLAN, Virtual Local Area Network, and we can have them in different physical locations. And that's what this is supposed to show here. We have the engineers over here, QA here, maybe in a different room, maybe in a different building, in a campus, maybe on a different floor, doing different things, but they're all on the same IP network by using VLANs. So the network layer creates broadcast domains. Broadcast domains using the temporary addresses, the IP addresses, that can change. Allows larger networks, reduce congestion, and prevent switching loops. What I didn't show is that if we connected a bunch of devices together in a loop with a switch, you're going to shut the broadcast, you're going to shut the network down because you're going to get a thing called a broadcast storm. The layer 2 has no way of stopping packets except for this protocol that was the amber there that took us so long to get on. It's called a spanning tree protocol. A switch has, and we saw in the Wireshark, it had the TL, the time to live. how far will it go before the packet dies? And if it can't find a home after whatever number of hops the TTL says it is, and each of the operating systems is going to be a little bit different, it just goes away. It dies and sends an ICMP message, the Internet Communications Protocol, back to the origin that says that the packet died en route. Couldn't get there. More intelligent protocols uses the routing protocols and the logical protocols. Two routing and routable protocols. Routing protocols, which is the word in the slides, are the protocols, the language that routers use to communicate with each other, to share information. Routable protocols are IP that allow us to get from one location to another location. Routers join two broadcast domains, separate subnets, networks, IP networks, can be specialized devices or general purpose routers, aware of the surrounding network structure and communicate with other routers. They could communicate to share information. What they really know when they start is what's connected to them, and then they share that with their neighbors, and their neighbor shares it with the neighbor, tell a friend who tells a friend who tells a friend, and pretty soon everybody knows how to get to the networks that are connected to you. And that's what the routing protocols do. Different routing protocols have different methods to share that, but their purpose in life is to share route information so that the data can get from point A to point B. IPv4, the IP packets, header and the payload, the TTL. And if we go back to the Wireshark, let me get it started again, maybe. Go back and look at it. Fragmentation attacks. We'll look at some of the switches while we're in here, or some of the markers. If we go down here, and let's see if we can find something that actually is a data. Now this says it's HTTP, has some HTTP. The IP protocol, and that's where we are, right? We say that it has a IPv4, the replacement is IPv6. I didn't have any IPv6 traffic in this one. It has fragmentation attacks. So what we have here are flags, and it says we have more fragments. And the fragment offset. It doesn't say this is the last fragment. So the insecurity here is that a hacker could insert fragments into the transmission and add information to that particular connection. The fragment offset says how far into the data packet this goes, how far into it, how much is it going to be, how far into it. The safe way around this is don't fragment, so we don't have the fragmentation to happen on these things. We said we had a time to live. TTL here, time to live 128. So this is going to be 128 hops. And this will prevent loop, because after it goes 128 hops over 128 routers, it's just going to go away and send a message back home and says, hey, I can't get there. And then the next protocol, when we look at those. IPv6, it says negotiates packet size before it goes, and that will prevent some things that go in here. These initially negotiate a window size between the two devices. And that's how much data, instead of sending it one data packet at a time, we send a group of them. You know, kind of like instead of driving everybody in a two-seater from one place to another, you put them on a bus so that we can send more information from one location to the other. They negotiate the window size. That doesn't mean that all the routers between them can handle that window size, and that's where fragmentation comes in, and don't fragment. IPv6 negotiates that. It looks at the entire path before it goes from one to the other, and sets a packet size so that there's not going to be any fragmentation. So we have the time to live, the header, and the payload. The header here, I know I keep flipping this back and forth. The header here, the IP header, is the IP information here, the source and destination address. We also have other things. The TCP is part of the header. Ethernet's part of the header. These are all headers that are part of the system that we're using here. Let's see. And say we have the IP, and then we have the data here, which is encapsulated in all of the header information. The header information, lots of information to get the data from point A to point B, and then we talked about the time to live. The TTL, when it expires, then it's done. It goes away. ICMP is used for error control in messages. That's where the expired en route would come from. Needed for the core network functions, and it can be used for a lot of attacks. It's actually used, they call it a ping sweep, to check to see which IP addresses are available that are answering the pings, and addresses may or may not respond to ping when we do that. It includes several messages. Determine how many TT. No, the ping doesn't. The number of hops. No, each of the operating systems is going to have a little bit different number of hops. Juanita. IPv4 determine how many TTL hops you have. No, the devices themselves, and you can when you start configuring routers, you can specify the number of hops that are available if you want to do that. If we look at let's look at a Windows, it's going to be different. Ping. See here, the TTL is 45, and we get a little bit of information. So the TTL is going to be a little bit different for each of the operating systems. And I don't have a Linux machine. It's even different than the Windows machine. Host unreachable. If I try to ping something that doesn't exist, and let's see if we can do that. And this probably will actually. I had to pick one, so we have a different TTL here. How far we're going to go, the time to live, what's left over. Ping u dot me. Apply from. Now, how can I manage to do that? Ping none. And hopefully, eventually, it's going to give me an error message back. Ping request could not find the host. Please check the name and try again. Going to get a little bit different message again for each of the operating systems. Host unreachable would be the standard reply for this if that host didn't exist. A source quench message, if we start sending too much data, we're back to buffers again. When the information comes in, we're going to maybe get too much at a time, and the receiver would say, hey, you're sending it too fast. It would send a source quench message that says slow down. A redirect is something that can be used for an attack. A redirect says, hey, I know a better way to get there. Kind of like somebody tells you about the shortcut that doesn't work. But I know a better way to get there. And the redirect may go through a hostile to get there. Time exceeded, that the time exceeded error message that we've taken, or the data's been there, can't get there, taking too long to get there in order to do that. Router advertisement and solicitation, which is used predominantly really in IPv6. IPv6, the router sends you the network address and you create your own host address for these things. And the solicitation, the router didn't send you that. The solicitation says, hey, router, tell me what it is. So what the solicitation says, router, send me a router advertisement. Wireless access points, layer 2, works like a hub. There's no broadcast domain separation in these things, and anybody that's in range can see you and try to connect. we have fat access points and thin access points, lightweight access points. The ones that are called fat access points are like you and I have, that you use a web interface to go onto it to do the configuration. A thin access point or a lightweight access point is configured centrally so that we have consistencies with them. We have ad hoc with a picture over there on the right. All of the access points connect with each other. There's no central device that they all connect to a wireless router or a wireless access point. The difference between a wireless router and a wireless access point is the access point just connects to the wired network. A router will route to someplace else. A standard, the 802.11, has a scaling issue. There's a limited number of wireless devices. Wireless uses a collision avoidance media access control where the device sends a request to send and the access point sends a clear to send. So you have to get permission to send on these things. Mesh networks, and a mesh network is everything talks to everything else. Cisco has a bunch of the routers that can automatically set up a mesh so that if one of them goes down, you have an alternate path to go from one location to the other location. Infrastructure, we have an access point ad hoc. They all connect to each other. The signals, we have predominantly two frequency ranges, the 2.4 gigahertz, which has been around for a long time, 802.11b, G, N, all had the capability to do that. The routers say that we have, 12 channels, I think, 14 theoretically, but you can't use 14, and I don't think you can use 13 in the U.S. They're used in Japan and Europe. The only clear channels in what the picture at the top is supposed to show is 1, 6, and 11. All the others overlap with each other. Most common, relatively long range, wide availability, small number of channels, small number of clear channels, 1, 6, and 11. And that's numbers that, those are kind of things that you may want to make a note of. The 5 gig are newer. 802.11ac only uses 5 gig. 802.11n, the A and B kind of started out at the same time. A used the 5 gig, B used the 2.4 gig, but apparently when they got ready to manufacture the 5 gigahertz higher speed NICs, they couldn't get the silicon, so everybody started buying the slower 10 megabits per second versus 54 megabits per second, 2.4 gig, because they were available for the wireless. When we got to 802.11n, it could use both of these, and then 802.11ac, the new one, only uses the 5 gig. The 2.4 is going to have a longer range. Generally in wireless, the higher the frequency, the shorter the range. And then the 60 gig, the new development, very high, requires a clear line of sight, can't pass through walls, but it's going to have a very, very high, or does have a very, very high data rate. Antennas that can be used, we've got the omnidirectional, the one that you see, the little rubber ducky that we have on the wireless access points, or the wireless routers that we have, and then directional antennas. The directional antennas are going to focus the signal and they're going to go further. The flat patch, and I've tried to get some pictures of these here. The flat patch is up here on the right. The dish parabolics, the one under it. Yagi is in the bottom right, and then homemade antennas. And there are a number of them. There's and you can go on the internet, and the Pringles can antenna. You can build your own if you want to do that. The directional antennas focus the signal, get a longer range, because you actually, by focusing instead of having an omnidirectional, you can have a stronger signal to go from one to the other. This is just some indications of what the radiation pattern would be with the different antenna types. So the convergence that was in the objectives, here we have telephony, industrial systems, surveillance, HVAC, data storage. What we're doing is taking these formerly standalone areas and bring them into the IP world. Sometimes good, sometimes not so good. Industrial systems, that's how the Stuxnet virus got into the Iranian controls so that we could destroy their centrifuges. HVAC, that's how the hackers got into Home Depot, through the environmental systems, because we're controlling them over the internet. A technician lost control of his password, of his credentials, got into their foothold, moved on into the system itself. Telephony, voice over IP. And then surveillance, we've got, the Ring doorbell, we've got cameras all over the place, monitoring what's going on. And a crime happens, an accident happens, you see it on the news. You can see from this camera what's going on. They have accidents on the interstate around here, lots, and oh, look at the traffic jams. You can see the traffic backed up from here to there for whatever else. People and a lot of the police, I guess if Ring gives a break, or you get it from the police department or something, if you will allow them to use your surveillance cameras. So these things are all coming together. And then data storage networks, iSCSI, we looked at what we have are remote hard drives, basically, that multiple users connect to. And you may have one at home. You can plug them into your router typically, and you can store stuff there. You can store the movies there, distribute the movies around the house, do different things with the data storage networks. Voice over IP, the things that we gotta have, an IP phone, looks like a normal analog phone, but it is designed to run on the IP network. And the image at the bottom kind of represents the things that we have to have. The call agent replaces the logical functions of the telephone exchange, manages the connections and routes the calls. The media gateway connects the PBX to the outer, or the PSTN is publicly switched telephone network. So it's going to connect us to the PSTN, the analog phone network. Application server, additional services, it may have voicemail, advanced services, and the multi-point control unit allows you to have teleconferences on the VoIP network. So VoIP, voice over IP, industrial controls, SCADA, systems control and data, large-scale distribution systems, information gathering, and some limited control, centralized control of manufacturing processes is where we're going to. The DCS, distributed control systems, and if you remember from Network Plus, these are primarily associated with refineries. They have direct control with limited information gathering. They are process controls. They monitor, and this is probably how, it's not probably, this is how they got into the centrifuges with the Stuxnet, that they infected the remote control, the remote management systems, and what it did was the virus oversped the centrifuges, burned the motors up, while at the same time sending a normal operation signal back to the supervisory control information. Neither of these things, none of these things are designed for security. And when we put them on the larger network, convert them to the IP network, then the security has to be added. The security is not there unless it's added. The environmental controls, same way. We had remote environmental controls. They installed them, and oh yeah, if you wanted in the summer, if you wanted to lower the temperature in your room, you had to go through a whole bunch of paperwork to get somebody to connect to the environmental controls and lower your thermostat by a couple of degrees. I think we could change them within 4 degrees of whatever the set point was, but anything greater than that had to come from outside in order to do those things. Network storage, and this image represents 3 different ways to do these things. DAS is direct attached storage. That's the hard drive that's connected to your computer, connected to the server. Network attached storage is a hard drive with its kind of very minimal operating system that's attached to the network. And a storage area network uses a little bit more sophistication and virtual hard drives in order to allow users to use centralized storage. What I like to think, and we used to use iSCSI, these were connected via the NIC. These were connected maybe a USB, and these are going to be directly connected to the device. Direct connect to the device itself. So different ways to add storage to the networks for these things. The direct attached, network attached, and then the storage area network. So we did finally get to the end of the first one. So what is the order of the OSI model from top to bottom? So, from bottom to top, I'm sorry. Bottom to top. Please do not throw sausage pizza away, all right? Somebody going to do this one? Since you already know it? Okay, yeah, D, B, C, G, F, E, A. So this portion is network addressing. We're going to talk about IPv4 and IPv6. Little overview during the break. But you know that's basically the bottom line. How many addresses? Yeah, the formatting's a little different. It's a little bit more efficient. It checks to be sure that it can get from point A to point B, that the window size is correct. It's more efficient. IPv6 is has more security associated with it than IPv4. And then we'll talk about address resolution and then network address resolution that allows us to use what we use or call private IP addresses, IPv4, on our private networks. The IP address itself has broken down, and this shows 3 classes. So when we first started out in the networking world, we had what we call classless or classful. Let's call it classful. Let's get the terms right. Classful addressing. We had classes that we could use A's, B's, and C's. And the addresses that were available had different octets. And the octets, because we have 8 bits in each of these, what are called dotted decimal notation, DDN, or dotted quads. We have 8 bits here. So the numbers that are available in each of these is 0 to 255. The Class A addresses had a limited number of network addresses, and that's what the blue represents, and somewhere around 16 million host addresses. And if you think about that, are we going to put 16 million addresses on a network? Yeah, probably not. The Class Bs had 2 of the octets that represented the network, and routers find networks. And then IP addresses find networks, network addresses, and then MAC addresses find individual workstations. In each of these, there are like 65,534, I think, addresses, networks as well as addresses. And here we have I don't remember the number of networks, but we have 254 assignable addresses on each of the Class C networks. These things have an address, and then they also have a thing called a subnet mask. Subnet mask associated with it. The subnet mask tells us how much of the address is network and how much of it is host. And we might have something like 192.168.1.6 and a 255.255.255.0 for the subnet mask. 255, trust me, is all ones in the binary. So in the subnet mask, wherever there are ones, binary ones is going to be network. So we can extend these things. We can also write it this way, or we can write it in a thing called CIDR notation. We could write this one as 192.168.1.6/24, which says there's 24 ones in the subnet mask. So if we did 8, 16, 24, that would be right. If we then extended this thing, so like 25/25, our subnet mask would be 255.255.255.128. And how did we get that? Because we have placeholders for these digits. And the placeholders, the value of these things, start over here on the far right. 1, 2, 4, 8, 16, 32, 64, 128. If you add all those up, it's going to be 255. So any place we have a 1, we would multiply that 1 by whatever is there. A 0, we multiply it by 0, and of course it gets 0. So this one would be 128. 128 plus 0 when we're converting it. And if we had a 1 here, it would be plus 32. And on down the line, 0, 0, 0. And let's do a 1 here. So it would be all plus 0 plus 1. So it would be, 128. 8 2 is 10. I'll carry 1. 6 be 161 would be what that would represent in decimal for these things. The subnet mask has to be consecutive ones when we write it, but it tells us how much of the address is network so that the routers can figure out where to send the stuff and how much of it is host, so that when it gets there, we know what the IP address is of the host so that we can find the MAC address of the host. So the Class A and the Class B and the Class C. The subnet masks, as you might guess, for the Class A is 255.0.0.0. 1 octet is network, everything else is host. The Class B is 255.255.0.0. And here is 255.255.255.0. So the 0 here, if we do 2 to the 8th, 2, 4, 8, 16, 32, 64, 128, 256. So it's 0 to 255 is 256 numbers. Zeros represent something in networking. In this case, the 0 is going to represent the network address. The network address is where the host bits are all zeros, or is 0. If we're not getting into subnetting here, but when you do that in the network portion, it doesn't always have to be 0. So the IPv4 address, 8 bits, 8 binary bits, dotted quad, dotted decimal notation. We can convert the decimal to binary, binary to decimal in order to do these things. A little bit better look at the class full versus the class less. I said that originally they were class full. Class less, we can use the subnet mask, and we can change the subnet mask from the class full ones, from the 255.0.0.0, the 255.255.0.0, and we call that subnetting. We move the and that's why I put that in there. There's some videos that you can watch, Juanita, that might help in the IPv4 portion of that. The Security Plus doesn't go into nearly as much detail as the Network Plus does. And I don't know how many have had experience, and I said earlier when we started, how many have had experience or the Network Plus class. I know the ones that were in my Network Plus class, and they're probably still beating their heads about subnetting. But yeah, we just mark off how much of it, and after you do it a while, it's like, you know, this was Greek when it started, and now I've made it German or something like that. It does get a little bit better. Yeah, Lisa says she's still shaking her head. It is something that in reality, you got to know it for cert tests, and that's about it. In reality, we got private IP addresses. So if you got all those private IP addresses, why you really need to subnet? Raphael still wants somebody to take his test, although I think he's probably in pretty good shape. Anyhow, the address is the first octet in the class A, 0 to 127. And the first bits here are to, if you don't remember them, and I always like shortcuts, but the placeholders are 1, 2, 4, 8, 16, 32, 64. This is just, and 128, this is just how much each of these places is worth. And if you do money, you do the same thing. We got pennies, we got dimes, we got dollars, we got tens of dollars, we got hundreds of dollars. So if you wanted, you know, change for $1, you'd have, you know, 4 quarters or whatever. We break our money up. We're doing the same thing here when we add stuff up. If you had $15, we have what? Ones. You would have 5 ones and 1 10. Here, if I add these things up, I can, since it's binary, I can only have a 0 or 1. I can either say yes or no for it. So we add these up to get the decimal because we like to use decimal. I can't think in binary. I knew a guy that could. I can't. So we want to look at what things are. If we want to convert from, and let's do a conversion here, convert from decimal to binary, we need to write this in binary for whatever reason. Let's say that we had 210. So what we would look at is this over here and say, is 210 greater than or equal to the first bit here, 128? And we'd say yes, so we put a 1 here, right, 128, and subtract it, and that's going to be 2, 8. Is that right? 8 2's 10, I'll carry 1, 8 2's 10, 11. 82. Is 82 greater than or equal to 64? Yes, it is. So then we would, 82, we would subtract 64 from it. 8 here, and then 1, I think. So is 18? Nope. Is it greater than or equal to 16? Yes. And we have a 2, so we can do 0, 0, 1, 0. So that's what 210 would be in binary. If you add all those up, hopefully you're going to get 210. One of my stupid checks for me is that, you know, 210, it's an even number, so it doesn't have a 1. That's a good thing. If it's an odd number, it's always going to have a 1 in here. So what these things represent, the first bit is 0, so it'd be 0 to all 1s after that. And if you add 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, it's going to be 127. The next one is 10. So it goes 128, 1, all zeros is 128, and then 1, 1, 1, 1, 1, 1, 1, let's see, we're going to do 191. 1, here it's going to be too many, so it'll be 1, 0, yeah, 1, 0. Add all of those up, we're going to get 192. The easy way that I remember it is I just go to the next one. 128 plus 64 is 192. Subtract 1, and it's going to be the last one available and the one before it. Class D's and E's, D's are called multicast, which goes to, instead of an individual, these up here, except for the broadcast address, which we saw a little earlier, goes to everything. These go to subscriptions, we'll just call it subscriptions, go to a group. And the Class E they call it experimental and military and all sorts of things, but the bottom line is we can't use any of these. We can use the A's, the B's, and the C's, the B's, and the A's to assign addresses to. I know that's another really big fire hose, and that this lesson tonight is a really big fire hose on networking. We have some special addresses. The 0.0.0.0 represents an unknown or any network. The all 255s represent broadcast addresses, and that's all network broadcast. The loopback address is a special address used for troubleshooting the 127, the network portion, 127.0.0.1. So we took 16 million addresses. We use one that says 0. The address that we use is 127.0.0.1, which is the local host is available to it. We also have private addresses that we can use inside of our network and don't have to buy them. And those are called private addresses. The 10 for the Class A's /8 has 8 bits in its subnet mask, which is 255.0.0.0. 172.16 is a little different. It has 12 bits, which is going to be 8 bits in the first one and then 4 in the next one. If we had 4 bits in the next one using our 1, 2, 4, 8, 16, 32, 64, 128, it would be 1, 2, 3, 4. If we add those up, 192, 224, 240, 240, I think, 240, not 250, 192, 224, 240, yeah, 240 would be it. So its subnet mask would be 255.240.0.0, the Class B. The Class C, the 192.168 address, and it says 17, should be 16. It uses the whole 192.168 address, but we mask it as a C with the 255.255.255.0, which says a network host. So we have 256 addresses, but we have to subtract 2 of them because we have to reserve one for the network address and one for the broadcast address when we do those. PIPA addresses are bad. 169.254. If you get those addresses, that means that your computer tried to get an automatic address from the DHCP process. We're going to look at DHCP here in a second. And it couldn't find a server. So it gave itself an address that can't go anywhere. But it's got an address. It can actually talk to everybody else that's inside that broadcast domain with a 169 address, but that's it. So IPv6, and this was a question a little bit earlier, what's the difference? And the massive address range is the big one. IPv4, 4.29 billion addresses. That's a lot of addresses. They're all gone. They're all in use. IPv6, 340 undecillion. That's the number at the bottom of the page. One of the numbers that I've heard, how many are that? Every human who's ever lived could have 5,000 addresses. It is more efficient. It has more security. It says compatibility issues, and the compatibility issues are that we're transitioning, and there are a number of transitioning intermediate steps. The biggest one is called dual stack, and in dual stack we have both IPv4 and IPv6 running on the machine. If you're running IPv6 at home, that's what you're going to be running. That's what I'm running here. My ISP gives me an IPv6 address. IPv6 doesn't have any private addresses. Everything is what's called a globally routed or a global address, a globally routed address. The private addresses that I do really quickly because, again, this is an overview, can't be routed on the internet. And we're going to look at a process of how we could use those in a minute called NAT, where we translate a private address to a public address to be able to get information off of the internet. The IPv6, this is what one looks like. The one up there at the top is called FE80. It's called a link local address. All link local addresses start with FE80. They're not MAC addresses, but they're used for local communication. If I had my computer here and my router over here, and each of them has an FE80 and they do FE80 address, FE80 address, instead of using the IPv6 address, the global address, as the default gateway where I'm going to send it, I'm going to use the link local address, the FE80 address. So it's used for all local communication, and I think that I can show that here, I hope. If I go on the IP address on this machine, I have an IPv6 address, and down here I have a link local IPv6 address. It starts with FE80. My default gateway here for the IPv4, 192.168.1.1, an IPv4 address. For the IPv6, it's a link local address that is used for that. So link local addresses starting with FE80 are used for all communications within the broadcast domain, I guess, the local link to go to the router. And that is, again, what one of the IPv6 addresses looks like. We can simplify them a little bit, and the way we can simplify them, the addresses, the ::1, let me do some things here. What we can do is, if we have an address that looks like, let's see, FE80, and they're separated by colons, 0017, :0000, :0000, and then we'll just say : just we have some other stuff here. If I have leading zeros, I can drop them. So we could have FE80, and then it'd have to have something else in here, :17. And if I have a series of zeros, I can represent them with a : one time. So I did that, and then if I go down here, let's just continue this one, : 17, 3, 6, : 0000. If I did that, : and then I would have my 1736, and then I have already used my : once, but I can do drop the leading zeros, and then again keep going with this thing. So we can shorten them a little bit. The link local, the FE80, which we looked at, is equivalent to the APIPA address. APIPA is automatic private IP addressing, which means that we couldn't get one automatic address. Site locals are available. They're routable within the site, not routable on the internet, or deprecated. And they come and they go, and the name comes and the name goes. Global start with 2000, and mine was a 2605, as I recall. Global are routable on the internet, so that we can use them to get information. Multicast and multicast go to, we'll call it subscription, but yeah, let's call it subscription. Or a group. A group always are going to start with FF something, FF02, : and these are going to be routing protocols, FF02 multicast, to do those things. Multicast go to a group of machines. Unicast go to an individual machine. Broadcasts go to everybody, to all of the machines that are in that IP network. Address resolution protocol, and we talked about that the final delivery is to the MAC address. The protocol that we translate the layer 3 to the layer 2 is called ARP, Address Resolution Protocol. And if I look at the ARP-A on this one, I got this is the actual real interface that I'm using. It says that my default gateway 192.168.1.1 has a MAC address of A0807836 F43A. Dynamic means that it discovered it. If it reuses it, it renews the timer. These things do time out. Another IP address on this network and its MAC address. and on down the line. This is my remote machine. We're going to look at a DNS server here in a minute. Is here also. So the ARP protocol finds the MAC address of the destination IP address and sends it there, because if we go back to when we looked at the switch had port to MAC address mapping to send it to an individual location. It caches the IP to MAC relations. Each of the protocols, each of the operating systems keeps it for a different amount of time, but it's not long. It's just for a few minutes, maybe. Some of them are like 2 or 3 minutes, some up to 10 or 12 minutes, depending on, and part of it depends on whether it's been reused or not. When it gets reused, the timer gets reset and say, yeah, I used this, I may need it again, so it keeps it a little bit longer. Caches these things short term. ARP poisoning attack. It's a great way. ARP's a stupid protocol. It is a great way to do a man-in-the-middle attack, because I just advertise my MAC address as the default gateway. And then I am going, when people are going out of the network to the one, in my case, 192.168.1.1, the router, they send it to me. And I can look at the information. And then I forward it on. IPv6 uses the neighbor discovery protocol in order to do that. It finds the routers and then the maximum transmission unit value. It determines how much data can be sent across the path before it actually starts sending the data. A little bit smarter in that way. IPv6 doesn't have broadcasts. It uses the neighbor discovery instead of broadcast packets to do these things. The DNS is the thing that allows us to use names instead of numbers. And what I want to look at is a DNS server here real quickly. What the hierarchy down here shows, if I'm going to go to some place, and I think I could probably just show the hierarchy in this server here. Wake up server. What it does, and I'll really confuse myself. I have the DNS running here, I think. I had to wake the machine up, so it has to get itself going. So what we have is the root, represented by the dot. The root's at the top of everything. Underneath the root we have top level domains. The top level domains .com, .net, .org, .mil, all of the end things. Here .uk is the United Kingdom. .us, .ca for Canada. And you see .tv for a lot of these places. It's not television, it's Tuvalu, which is a country code to do those things. Underneath each of these we have the domains that we use. We got Facebook here, LeaderQuest Online, different areas, ESAA here, and you notice it doesn't have anything. We're going to look at some of these. And underneath them, I want to go to one that actually has one, .net. Where's my .net? Yeah, there's my .net. I guess that's where I was, huh? Underneath them we have the IP address. We have what's called a host record, the A records, that contains the IP address of this case of www.ccesc.net. When I want to look something up, the first thing that the computer is going to do is look in its local cache and see if the address is there. If it's not, going to ask the local DNS server. If it's not, we have the root here, the dot. Underneath it, we have we'll just say the com. Well, let's do net because we'll do LeaderQuest maybe. Net. Under net, we would have maybe LeaderQuest, and then we would maybe have the server that was listed in here. So if we wanted to go to www.leaderquest.net, And our DNS server doesn't know where it is. It goes to the root and says, hey, I need the address of www.leadrequest.net. It sends back a message that says, I don't know that, but I know the address of the .net DNS server. So we get the address of this DNS server. We then go to it. I need the address of www.leadrequest.net. I don't know, but I can tell you the address of the LeaderQuest DNS server. We go to the LeaderQuest, and it says, oh yeah, the www is 72.16.12.47 or whatever it is. It sends that back to us. We now have that IP address. It gets cached in our computer, and when it gets cached, it stays there until we restart the machine, so that we don't have to go through this process again. It also gets cached if we're using this DNS server in this DNS server, and a number of these are there. They are cached. These things time out, because this says time to live. In this case, it says what? 0 days, 3 hours, 59 minutes, and 51 seconds. So when that happens, this record will go away. It'll have to be looked up again. That's so because IP addresses change. IP addresses might change. So DNS, this is what a DNS server actually looks like. The .com, a bunch of stuff in here. We got a host monster. I'm going to say ESAA. ESAA uses a thing called a CNAME, which is a something else. And it says that it's at www.esa.com.cnd.cloudflare.net. Cloudflare is the outfit that went down the other day in a whole bunch of places, a whole bunch of locations did go down. And see, what was that? I always forgot where it was. It may have timed out already. It was CDN, right? cdn.cloudflare.net. So we'll go to the .net, the Cloudflare, the CDN, the COM, and in the COM we have ESAA, and here we have the records for it. So 104.24.114.59, the A record. This is the IPv6. It has an IPv6 address also. So the IPv6 are 4A, quad A records are DNS records, the lookups for those things. The next topic, I think, is DHCP, and while I'm here, DHCP, Dynamic Host Configuration Protocol, and I thought I had one, maybe I don't have one running on here, is a protocol that allows us to automatically assign IP addresses. Let me see if I can move this thing back over and maybe install one of those while we're talking about it. So translates FQD and fully qualified domain name to IP address. IP addresses are the things that we need in order to get there. DNS poisoning. If DNS can be poisoned, if I can poison DNS, then I can send somebody to the wrong location. DNS security, DNSSEC secures DNS to do those things, so that we can have secure DNS. By default, it's not secure, but we can use, and it's not something that is used in a lot of places right now when we do that. DHCP contains a pool of available addresses on it. The addresses are assigned dynamically or by reservation. DHCP server can have DHCP options, and if the server is not available on the client's local segment, the routers can send. It's a broadcast protocol. Routers stop broadcasts. So if we have an issue with it, then we're not able to go across the router in order to get from one to the other. But DHCP, and this is not going to install easily. Let me get rid of that one. I was trying not to start this other virtual machine, but I will, and we'll look at it here in a second. Let me just get this going, and then we'll go on with the slides and come back to look at what DHCP and the DHCP configuration might look like. Address translation, we had those private addresses that we can use on our private network. What the private addresses are not routable on the internet. The public addresses are. So we use a process called NAT, Network Address Translation, where we create the NAT table, and what this shows is from 192, 168 to 120, whatever, we translate the 192 address, the private address, to a public address. And it goes into a NAT table. A NAT table. And TrueNAT has a one-to-one private to public. We can have a NAT pool where we have a pool of addresses, because you figure that not everybody's going to be on the internet at the same time. So we only use part of them to allow our users to go on the internet. Or we can have this other thing called PAT, Port Address Translation, which is what you and I use. We use our private address. I have a 192.168. I use the .1 network because that was the default. I just haven't changed it. I've got a 72 something on the other side. 72. We'll just make something like 16.12.6. So when I do this, TCP had port numbers, which we really didn't get into, which represented resources. Port numbers, an IP address, and a port number together are called a socket. So by using port address translation, I can create a unique location, IP address, and port number, or unique sockets. And I always think of a socket as a connection point. An IP address and a port is a socket. Does that, when we put the two together, we create a socket. And that's a unique location. If I'm going to a web server is port 80. And let's say that its address is 72.12.47.6. That, along with the port number, says, hey, go get this resource. So that then now goes to a specific, as I see, I can't spell it, a specific web server. So sockets are unique connections. And I think about them like maybe a light socket, or a socket that you plug something into. You plug something into a socket, an address and an IP address can do that together. You didn't get a whole lot, Alex. Go ahead and send it again. So sockets are used for port address translation. A whole lot more ports. 65,534 usable ports, a whole lot more ports than there are IP addresses that we have, so we can go to a number of places at the same time. And we can have a number of devices on our network at the same time. Because you probably have more than one computer on your network. You probably got a computer, I got a computer, got a laptop, 2 tablets, 2 phones, 2 TVs, all of them have IP addresses. I have a single public IP address. So I use port address translation to create the sockets to translate one to the other, one side to the other. The router maintains a NAT table in order to keep those things straight. I've got a DHCP server running here on this server. Just a real quick IPv4, and I'm going to create a new scope, and a scope is the listing of IP address. I'm going to delete this one, and then we'll go in here and do a new scope. And the thing, we can name it, we'll name it Site Plus. And we can have a description of what it goes to, whatever we want to do with that. The starting IP address. So we're going to tell it what IP addresses that, I don't want to use a 1 here. Yeah, we can use a 1 here. What I'm not going to do is activate it so it messes me up. 1 dot, I got to have something here, 200, let's say 170, that one works, 170. And we'll say 192.168.1.220. Those would be the addresses that this thing would hand out. You notice that it automatically, because it knows that 192 is a class C, it automatically put in the subnet mask for me. Starting address is not valid. 192. Well, because I made a typo there. 192.168, because the starting address was now above the ending address. I can have exclusions if I don't want something given out by this one. I can put an exclusion in here, 168.1. Let's say 200 to 192.168.1.201. We'll have a couple addresses in there that it won't hand out, so we can have exclusions in this thing. We get a lease. How long is the lease? The default here is 8 days. I can change that. Depending on how frequently I want them to expire, I can change the lease for these things. Options, and let's look at some of the options that we can do in here. The router, the default gateway, 192.168.1.1. So we can add the default gateway, gets that automatically. The DNS server, let's say it's 192.168.1.1. The DNS server gets here automatically. So now I can resolve things. A Win server, Windows Internet Name Server, probably not used for anything, and we're not going to put anything in there for anymore. Do I want to activate it? No, because I don't want it giving out addresses here. So when I look at it, I have the address pool, the addresses that I've given out, the exclusions, and if I had any leases, I could have them there. I can also reserve an address. If I wanted 192.168.1. Let's say 210, I could have new machine, but then I'd have to type in the MAC address, and I don't have a good MAC address over the top of my head. That MAC address would get that IP address all the time if we did a reservation for those things. So the scope options show up here. There are others that are available, lots of them that are available. Time server, NTP server if you want to do that, name servers, cookie servers, all sorts of things are available for DHCP. DHCP, and what we usually say, it gives out IP addresses. It gives out IP addresses and other information that you need for these things. The NAT methods, the one-to-one, one private address to one public address, one-to-many, which is going to be 1 to 10 going to the many privates, and I don't like the way they did this one because they're all private addresses, but that would be port address translation, so that we have the NAT table. We're going to have addresses going to this one. We're also going to have ports associated with it in order to create sockets for these things. PAT, and this is the PAT is, if you notice, the PAT here is the one-to-many. So port address translation, we have port numbers associated with these things to create unique locations called sockets. So an IP address and a port number creates a socket. Let's go ahead and finish up. Some of this we've already talked about. TCP or UDP, network ports, common network applications. So the transport protocols are used for end-to-end communications, one location to the other. TCP, Transmission Control Protocol, reliable, the three-way handshake. It is numbers the data as window size to so much. UDP, user datagram protocol, it doesn't do all of that. It doesn't have as much overhead as TCP has. Use ports or sockets for host level multiplexing so that we can have more than one connection to one location, or that we can use it for port address translation. If we wanted to have a connection to a web server and maybe an email server at the same time, we would need two connections at the session level. We need two sessions. We might go to the same location, but probably not, but we need two sessions. And that's where the ports or the sockets come in, because I would have a connection on my machine, let's say that in 192.168.1.27, and port 8000 might go to the web server, and then 192.168.1.25, port 9000 might go to the email server. So I can have multiplexing multiple connections going on at the same time. If I were translating these things in the translating device, they would come out with a public IP address and a port. My public IP address and a port. And that would be translated to one of these guys. And then I'd have the same public IP address with a new port for this second connection to go on the network. When the answer came back, it would go to this socket, to this connection, to get the information back to the proper location for it. So, TCP, connection oriented, we look at that. We looked at the three-way handshake. Connection oriented is called reliable because it verifies the data delivery. It numbers the data, and if it doesn't all get there, it says resend it. Detects and resends corrupted data. If something is corrupted or doesn't get there, it doesn't acknowledge, or a resend. By not acknowledging it, it gets a resend. Regulates the data rate. How much can we take at one time? And that's what the choke packets are all about too. If we're getting too much data, then we give a slowdown to come back. Sequencing keeps them in the correct order by numbering them. If they come in out of order, and that could happen, then they can be put back into the proper order. Kind of like sending the letters, numbering the letters from going back home on deployment, so that they can be put in order so that things make sense. The three-way handshake, I think we saw that. I know we saw that in the Wireshark, but the send says, hey, I want to have a connection, and here's the start of my numbering system. Host B acknowledges that, increments the numbering system, and then says, I want to have my own numbering system, the send, and then we acknowledge it. As we send data, we acknowledge it by increasing the numbers that go along with them. UDP, connectionless, and it says unreliable. Connectionless is a term that I like. Unreliable from the standpoint that it does not number, it doesn't do the three-way handshake, it doesn't establish a connection before we start up. It sends the data. The applications are going to be responsible for determining if something didn't happen. So we have that. Yes, Don?
The way that the TCP and UDP were explained to me was kind of like your mailman. With TCP, he delivers it to your mailbox. With UDP, he just kind of throws it in the yard as a lost box.
Yeah, you could do that. Or you could say, how about a return receipt required for TCP? And UDP would be first class. That where he throws it in the yard or puts it in the mailbox or whatever else. The thing about TCP is there is a receipt for it. And what you said, that works. The registered mail or return receipt, registered mail in that we have all of the controls that go along with it, would do that. TCP also numbers the packets so that they can be reordered if they need to be. But what he says, that's a good analogy. UDP, it's just, it's there. There's no acknowledgement that goes on with these things. It is designed to, and if you did a Wireshark of the meeting that we're having right now, they're UDP packets, because small packets, very small packets. If we lose one, not such a big deal. TCP can be really big. It's for things that need the acknowledgments that go on with them. Let's see, the network ports. And these are the ports, and these are the ones that go through. These are the ones that you're just going to have to look at, and this really does become, until you use them for a long time, a memorization exercise. Web browser, HTTP, port 80. FTP uses port 20s and 21. Telnet, port 23. Telnet's an insecure remote access protocol. The system ports, the ones at the bottom, they call them system ports. You'll also hear them called well-known ports. The well-known ports are 80, HTTP, 23, Telnet. What they got to be well-known was in the beginning of these things, that somebody wrote this really cool program and said, hey, meet me on port 80 to see my new web browser. User ports, 1024, 49, 151. These are registered. If you write a program and you need a registered port, you can register the port that your program uses. And then the other one, the private ports at the top end, ephemeral ports, temporary ports. Every connection in TCP and UDP has an address and a port number to create the socket. The ephemeral, the temporary, the ports that we get on ours for our source ports are going to be in that private ports range up there, or the ephemeral, the temporary ports range that does these things. Application protocols, the way we do this, restrict the plain text protocols, and those would be the Telnets and the FTPs of the world. Secure replacements for Telnet, SSH, secure FTP or secure FTP. Combine insecure protocols with others that provide security. And IPv4 is insecure. We use IPsec in order to make it secure. Lower layer security, VPN or Wi-Fi encryption can be used for those. And then network segmentation, the VLANs, or just separate IP addresses. Network segmentation, segment the network into multiple IP networks that give you a little bit of separation of things that go on. Some more ports here. Telnet, insecure text-based terminal connections, TCP port 23. Secure shell, SSH, TCP port 22. It's encrypted. It's the secure replacement for Telnet. RDP, the remote desktop protocol, uses port 3389, Windows proprietary remote access protocol. You can also, it has a remote, Linux has a remote desktop protocol. It's just a little bit different. It looks very similar to the Windows one. Simple network management protocol, UDP ports 161 and 162. 3 versions of SNMP that we can get information and send information. Version 1 and 2 are basically insecure. Version 3 is the secure protocol that's used with it. Some more list of ports. Lightweight directory access protocol, LDAP, port 389, secure LDAP, port 636. NetBIOS, broadcast protocol associated with Windows, TCP and UDPs 137 to 139. Server message block is the Windows folder sharing protocol, uses port 445. FTP ports 20 and 21. It's insecure, is being replaced by FTPS, File Transfer Protocol Secure, or SFTP. Those really are different protocols. TFTP, Trivial File Transfer Protocol, port 69. It's a simplified FTP. And then the Network Time Protocol, NTP, uses port 123. HTTP, HTTPS, HTTP, web browser, the unsecured one, port 80, HTTPS, port 443. Email protocols, and I told you this is a listing basically of protocols. The sending one simple mail transfer protocol uses TCP/25. Post office protocol, to retrieve email from the servers, it actually downloads them or can download them to your device, uses port 110. IMAP reads the email on the email server, and as a network administrator, that's what you want because you don't want emails going away. You have to back them up, and sometimes you have to archive them all, be able to recover them all, but IMAP uses port 143. MAPI is a proprietary Microsoft Exchange protocol. SMTP, POP, and IMAP are insecure, but they can use SSL, Secure Socket Layer, or Transport Layer security for access. This is something that has to be added to them to make them secure. Some tools, we've looked at some of the ipconfig is the one that I've been looking at to, I just want to do these, and then they've got slides for each of them, and I think that we can just do them. ipconfig gives us the ipconfig, the Windows configuration information for IP, and this is the simple one. ipconfig all gives more information. ifconfig does the same thing for Linux. netstat tells us what's connected to the device. I think it's -A. If I can find the dash. Shows me the TCP connections, listening or establish the connections that I have to something. Closed, I have an established connection, HTTPS to 107. You know, those go on and on and on and on. Gives you a listing of, and one of the ways you can check to see if something bad's happened to your system. NBTstat, diagnostic program for NetBIOS, not really used a whole lot. ARP we've looked at. NS lookup, name server lookup, uses, it's a way to test the DNS server to see if you're actually getting lookups. Ping, we looked up. Ping just checks layer 3. Ping, let's see. And I'm going to do this because this should give me an IPv6 address, and it does. The time, it gives you an idea of what's going on. Trace route. Let's do ccesc.net. Tells me what routers it goes through, and where it fails is going to be the router that has the issue. So it tells me the names of the routers, the IP addresses of the routers it goes through each hop, so you can see the number of hops that it takes to get there. So this is going over a maximum of 30 hops. When it stops here, this is a router that doesn't respond to it. What trace route does is starts with it. It gets an error message back. Depends on the error message. That one went a long way, 19 hops to get there. It sets the first one, it sets the TTL to 1. Goes to the first device. It says, oh, timed out. Error message comes back. Then it sets the next one to a TTL of 2. Goes to the second hop. Comes back with the error message of 3 on down the line. So it uses the TTL and the error messages in order to do that. Path ping is a Windows thing that does a lot the same as traceroute does, except it's really much slower, and gives you more information, but it is significantly slower than it. And these are just the slides of what they look like, what you saw on the other ones, and you can try each of these out. Netstat's one to kind of take a look at. NS lookup checks the NS, checks to see if it's resolving the name server, if it's resolving like it should. And then ping we've looked at, you probably used ping checks layer 3 to see what's going on. So we can do these. What I'm going to do is match the protocols. I'm just going to say, yep, the telnet's 23, SSH is 22, SNMP 161, SMTP is 25, FTP 21, FTP is 20 and 21. LDAP Secure 636, DNS 53, POP 110, IMAP 143. You're going to have to know some of these. And in the resource share is, again, a couple of documents that have some port lists in them that might be useful. So you want to securely connect to a server via command line terminal interface. What protocol would you use? Yeah, SSH, Secure Shell is the secure protocol. PuTTY is a client that you can use for it. Again, some of the things that you may want to play with. How many total packets needed to exchange for a TCP handshake? The three-way handshake for these things: the SYN, the SYNAC, and the ACK. What kind of communications would be suitable for UDP? Choose all that apply. Any takers on that one?